January 1940. A thin veil of winter frost clung to the windows of an aircraft factory on the outskirts of a growing American industrial town, muting the clang of metal and the hiss of welding torches that rolled through the night. Rows of half-finished fighter wings hung suspended in steel jigs, their aluminum skins cold to the touch, their internal ribs waiting for teams of exhausted riveters to coax them into alignment. Production was slow, painfully slow, even as Europe burned, and every military observer warned that speed would soon decide everything. Supervisors hunched over clipboards, calculating hours they no longer had, while the assembly floor crawled under the weight of a system too precise, too delicate, too dependent on painstaking human fit. Then, toward the back of the drafting office, on a desk usually ignored after sundown, lay a new blueprint, pencil-lined, clean, and signed by an engineer barely out of his teens. It proposed something no one in the building believed possible. A wing that could be built not through days of careful coaxing, but through a sequence so standardized that sections would lock together in minutes. Few noticed it that night, yet the pressure outside those factory walls was about to make ideas like this impossible to ignore. By the end of the 1930s, the world was tightening into two distinct camps, those preparing for war and those hoping it might somehow be avoided. Yet even the most cautious governments understood that the age of biplanes and cloth-covered wings had ended. The new generation of fighters emerging in Europe and America demanded precision engineering on a scale industry had never attempted. All-metal monoplanes with stress-skin construction required tolerances far beyond the reach of small workshops. Aircraft once crafted like bespoke machines now needed to be produced by the hundreds, then the thousands, if any nation hoped to maintain control of the air. And in every country watching the storm gather, one reality became painfully clear. The bottleneck was not aerodynamics, not engines, not even materials. It was assembly, specifically the wings. The wings of a modern fighter were no longer simple structures. They carried fuel, guns, ammunition, wiring, control surfaces, and retractable landing gear. They transferred the forces of flight into the fuselage and kept pilots alive in dives that pushed metal and bone to their limits. But building them required a level of precision so demanding that even slight misalignment meant hours of rework. In European factories already transitioning to wartime footing, teams of skilled workers hovered over wing spars and ribs, adjusting parts by eye, tapping them into place with soft mallets, trimming where necessary, drilling where unavoidable. It was craftsmanship elevated to national urgency, but craftsmanship did not scale. For every aircraft that rolled off the line, several more waited on incomplete wings that refused to fit without coaxing. Across the Atlantic, American industry observed these early production struggles with growing concern. The United States was not yet at war, but military planners watched the Battle of Britain with unease. The Luftwaffe's early advantages had less to do with pilot skill and more with raw output. Germany had spent years optimizing its aircraft factories for rapid expansion, even if some methods proved difficult to sustain. The United States, with its sprawling industrial base, believed it could eventually outproduce any rival. Yet the transition from peacetime manufacturing to precision aircraft engineering was proving far more complex than optimistic pre-war planners had predicted. Automobile factories could stamp steel at incredible speed, but they were not prepared for the intricacies of aircraft wings whose components had to nest together in exact sequence, measured not in eighths of an inch but in thousandths. Inside many American plants, engineers and production managers wrestled with the same problem. No matter how fast sheet metal arrived, no matter how many workers were hired, the assembly line slowed at the wings. Each one required hours of fitting. Each mistake multiplied delays. Blueprints provided the geometry, but not the human labor required to make reality conform to paper. And time, already precious, was becoming a weapon. Military officials delivered new forecasts that startled factory executives. If the war continued to expand, the United States might need tens of thousands of aircraft annually, a figure far beyond current capacity. Every inefficiency on the factory floor echoed forward into the strategic balance of the coming conflict. The culture of engineering at the time made innovation both essential and difficult. Senior designers, many trained in the age of wooden wings and hand-built aircraft, respected tradition and resisted untested ideas. Production crews valued repeatability and distrusted theoretical solutions that ignored practical realities. Drafting rooms were hierarchical, tightly structured, filled with the quiet scratching of pencils and the murmured debates of men who had spent decades mastering the geometry of flight. In such an environment, change often came slowly and less forced, and pressure was building. Reports from Europe described aircraft losses that demanded immediate replacement. Britain pleaded for more fighters under what would soon become Lend-Lease. Neutral nations rushed to rearm. In every direction, war signaled that the decisive battles of the sky would not wait for comfortable production schedules. The factories had to adapt, and they had to do it quickly. This was the environment in which the idea of faster wing assembly method, an idea that seemed naive, impractical, even impossible, quietly surfaced. It emerged not from a senior engineer hardened by decades of experience, but from a young draftsman who spent more time observing the rhythm of the factory floor than defending established doctrine. Yet the significance of his insight would not be fully understood until the consequences of global demand made it unavoidable. The world was shifting toward total war, and in that shift, even the smallest blueprint had the potential to change industrial destiny, narrowing the gap between need and capability with startling speed. And as the crisis deepened, attention would inevitably turn toward the specific plant where the challenge of wing assembly was becoming a critical point of failure. At the heart of one American aircraft manufacturer, a sprawling complex of brick, steel, and glass hummed with the relentless urgency of a nation inching toward war. The plant had expanded rapidly over the previous 2 years, swallowing nearby fields and warehouses as new workshops rose in long rectangular rows. Inside, the air smelled of oil, aluminum dust, and hot rivets. Conveyor belts rattled through corridors as parts flowed from machining rooms to assembly bays. Blueprints lay stacked in carefully organized cabinets, each sheet defining the exact geometry of components that thousands of workers attempted to bring to life. Yet despite the size and resources of the facility, a single recurring problem shadowed every production forecast. Wing assembly times were spiraling out of control. Airframes accumulated in back corners of the plant, fuselages resting awkwardly on sawhorses while they waited for the wings that never seemed to arrive on schedule. Production supervisors understood the cause, but had no easy solution. The factory's main fighter model relied on complex cantilever wings with multiple spars, intricate rib structures, and stress skins that had to be tensioned precisely to maintain aerodynamic integrity. Every deviation, every slight mismatch, every misaligned hole introduced hours of rework. Skilled workers moved from jig to jig with a rhythm born of experience. But experience alone could not overcome the inherent inefficiencies of a process designed without mass production in mind. The aircraft had been conceived by brilliant engineers, yet the factory, now responsible for building dozens per week, was bound by methods better suited to an earlier, simpler era. Senior managers discussed improvements, but most proposals required new tooling, new workflows, or changes to the aircraft's certified structure, all of which risked slowing production even further. In the drafting department, far from the clamor of the assembly bays, a different perspective began to take shape. The room was quieter, filled with the soft glow of desk lamps and the precise lines of T-squares sliding across vellum sheets. At one of the least prestigious tables sat a young assistant draftsman who had joined the plant barely a year earlier. He was technically minded and observant, the kind of apprentice who noticed details others overlooked. He watched the experienced engineers debate aerodynamic loads, stress factors, and structural margins, yet his attention drifted toward the practical disconnect between their elegant drawings and the messy reality unfolding on the factory floor. Most in his position kept their focus narrow, assigned to copying sections, revising hole patterns, or updating part numbers. But he had begun to notice patterns, recurring frustrations in the assembly bays that mirrored the rigidity of the drawings pinned above his desk. He listened to workers during his occasional visits to the shop to deliver updated prints. They spoke of ribs that never lined up perfectly without filing, of spars that required careful prying seat correctly, of skin panels that warped subtly under temperature changes. None of the issues were individually catastrophic, but together they formed a web of inefficiencies that stole precious hours from each wing. He saw workers improvising solutions, inserting shims, widening holes slightly, or adding temporary braces to force alignment, small acts of creativity that senior engineers often overlooked or even discouraged. The official documentation never recorded these micro-corrections, yet without them, assembly would have slowed to an even more painful crawl. Gradually, the young draftsman began sketching alternatives in the margins of his notebook. He was not trying to redesign the aircraft. He simply wondered why the process could not be simplified. What if sub-assemblies could be completed almost independently, without constant reference to the full wing fixture? What if alignment could be built into the components themselves so workers no longer relied on manual adjustment? And what if jigs could be standardized instead of custom-built for each phase of assembly? These questions were innocent at first, the product of curiosity rather than ambition. But as the backlog of incomplete wings grew and production quotas tightened, curiosity hardened into intention. One evening, staying late in the drafting room long after most staff had gone home, he began translating his scattered sketches into a coherent blueprint. He redrew rib sections to include standardized attachment points. He incorporated simple interlocking joints that would guide components into alignment before any rivets were driven. He reorganized the sequence of assembly into modules that could be built in parallel rather than sequentially. The changes did not alter the aircraft's performance characteristics. They merely reimagined how the parts came together. By the time he leaned back from the table, exhausted but satisfied, he had outlined a method that claimed something extraordinary, a wing assembly process measured not in days, but in hours. He knew the blueprint would face skepticism. In an environment governed by hierarchy and tradition, innovative process changes rarely emerge from the youngest person in the room. But the pressure from the outside world, the war, the rising demands, the urgency that seeped into every production meeting was tightening around the factory like a vice. And with that pressure, even the most unconventional ideas would soon demand attention, drawing the gaze of managers desperate for solutions they once would never have considered. The young draftsman's blueprint did not enter the factory as a revelation. It slipped quietly into the review stack on a morning when supervisors were already overwhelmed by memos, revised schedules, and escalating demands from Washington. Yet, even in its understated arrival, the document carried a tension that would soon divide opinions across the plant. The first angle through which this moment can be understood is the human one, the undeniable weight of hierarchy in an environment built on discipline and seniority. A teenager proposing a fundamental shift in assembly practice bordered on audacity. Many in the engineering office had spent decades mastering structural design, earning their authority through years of incremental improvement and accumulated experience. To them, innovation flowed downward from the top, not upward from the lowest rung. When the blueprint circulated during an internal review, some dismissed it with polite indifference, others with irritation. Yet beneath the skepticism lay something unspoken, the faint but unmistakable awareness that the factory was running out of alternatives. The pressure to produce more aircraft was intensifying, and tradition, no matter how respected, could not shield anyone from the reality that old methods were failing. Beneath this human friction lay the second angle, the production angle, which captured the quiet genius of the blueprint more clearly than any debate over rank or credibility. The teenager had done something deceptively simple. He had treated the wing not as a single monumental structure, but as a series of smaller, modular components designed to come together without struggle. In his drawings, each rib and spar carried not only its structural purpose, but a built-in logic that guided the assembly process. Edges aligned naturally. Holes matched without adjustment. Brackets seated themselves without persuasion. Instead of forcing workers to adapt to a design that resisted mass production, the design itself was reshaped to accommodate the realities of the factory floor. This was more than convenience. It was a transformation. By breaking the wing into sub-assemblies that could be built independently, the draftsman had learned to see the aircraft not as a finished machine, but as a sequence of operations. It was the kind of thinking that belonged to a new industrial age, one where efficiency was engineered, not merely hoped for. A third angle reveals why the blueprint was technically plausible despite its radical implications. The technological underpinnings of the idea rested on three interconnected pillars: jigs, fixtures, and tolerances. While senior engineers often focused on aerodynamics or stress calculations, the teenager had immersed himself in the mechanics of production tooling, studying how jigs control geometry and how fixtures constrain movement. He realized that if components were machined to tighter tolerances upstream, then downstream assembly would no longer require the judgment and feel of skilled craftsmen. Instead, the parts would lock into place with almost mechanical certainty. This shift represented a profound inversion of traditional aircraft manufacturing. Where older methods assumed imperfections would be corrected during assembly, the new approach demanded that imperfections be eliminated before parts even reach the floor. In essence, he placed the burden of precision on the earlier stages of production, enabling the later stages to operate with remarkable speed. The simplicity of the final assembly was not accidental. It was the product of deliberate, meticulous planning hidden beneath the clean lines of his drawings. These three angles, the human, the production, and the technological, intersected in tension across the factory. Workers gradually became aware of the blueprint, not through formal announcements, but through rumor. Some joked about the miracle wing said to fit itself together, while others scoffed at the idea that a teenager could redesign procedures that veterans struggle with daily. But there were also those, particularly on the floor, who understood instinctively what the blueprint represented. They knew better than anyone that the current process consumed far too much time and energy, that no amount of skill could overcome a design that refused to cooperate. For these men and women, the idea that someone was trying to make their work faster and less punishing held quiet appeal. Their acceptance would become crucial, for even the most elegant redesign remained theoretical until the people responsible for executing it believed it was worth trying. Yet beneath all of this movement lay another truth. The factory's struggle with wing assembly mirrored a global shift in warfare itself. War was increasingly becoming a contest of output, measured not in bravery alone, but in the ability to replace lost machines faster than the enemy. Nations with streamlined production processes would dominate the sky. Those relying on older, slower methods would fall behind. And though no one fully realized it yet, the blueprint sitting on those drafting tables represented more than an internal improvement. It offered a glimpse into the emerging future of wartime industry, a future where speed, precision, and modularity would shape not only aircraft, but the entire machinery of conflict. As discussions deepened and the blueprint began to attract cautious attention, another set of forces would soon come into play. Forces tied not to technology or production, but to leadership, adversaries, and the moral weight of designing tools for war. Those angles, equally essential to understanding the full impact of this transformation, would define the next stages of the blueprint's journey from an unlikely idea to a wartime necessity. Leadership within the factory became the next decisive angle in the story, for no idea, however elegant, could reshape production without someone willing to bear the risk of trial. The manager who finally paused long enough to study the teenager's blueprint was a mid-level engineer, experienced enough to understand the weight of innovation, yet distant enough from senior hierarchy to recognize when old assumptions were failing. He read the drawings with a mixture of skepticism and curiosity, tracing the modular sequences the draftsman had so carefully laid out. The proposal did not ask for exotic materials, new machining centers, or structural redesign. It simply reorganized the work. Still, Adopting it meant halting a section of the line, reconfiguring jigs, retraining crews, and sacrificing precious hours at a moment when even minutes were counted. Approving such an experiment exposed him to criticism if the trial failed. But declining it bore its own danger, the quiet realization that incremental fixes were no longer enough. In that fragile balance of caution and necessity, he made the decision that would later define his career, not out of ambition, but because the numbers on the production board made it clear that change was not optional. Beyond the factory walls, another angle shaped the stakes of this moment: the enemy's production capabilities. By 1940, the world understood that the air war was also an industrial war. Germany, Italy, and Japan pursued their own manufacturing strategies with varying degrees of efficiency and adaptability. The Luftwaffe, in particular, had surged early by standardizing aircraft and pushing factories toward high output. But even the Axis powers faced constraints: limited raw materials, skilled labor shortages, and production systems less suited to large-scale modularity. For the Allies, and especially for the United States, the opportunity lay not merely in matching enemy production, but in surpassing it so decisively that attrition would tilt the balance. A blueprint that shaved hours off every wing assembly represented more than an internal improvement. It became a strategic asset. Every fighter completed faster meant one more aircraft available for training, patrols, or combat. Multiplied over weeks and months, the cumulative effect would influence not only squadrons, but entire campaigns. In this sense, the teenager's idea fit into a larger, invisible arms race, one measured not in bombs or bullets, but in throughput. Yet efficiency carried a moral dimension too, forming another angle that quietly shadowed the blueprint's ascent. The draftsman had never set out to change the course of the war. He had simply wanted to solve a problem that bothered him. But as his idea moved from drafting paper to discussion tables, a deeper truth emerged. Making aircraft easier to build also made them easier to replace, and therefore easier to send into combat. The increased output would allow pilots to fly more missions and commanders to accept higher risks, knowing reinforcements would come. The logic of war demanded such decisions, but the human cost remained. Young men in cockpits, often not much older than the draftsman himself, depended on the speed of production to provide the machines that carried them into danger. The engineer's contribution, though grounded in geometry and process flow, was ultimately tied to life and death. This reality weighed differently on each person who encountered the blueprint. Some saw only the strategic necessity. Others felt uneasy at the acceleration of a mechanism designed for destruction. The teenager, inexperienced in such complexities, could not yet grasp how deeply his lines on paper would ripple outward. Still, in the realm of engineering and command, moral discomfort rarely halted progress. The pressure to act continued to build. Factories across the nation felt the tightening pulse of war in every telegram and every revised quota sent from Washington. The plant's senior leadership, once skeptical of unconventional ideas, now reconsidered any proposal that offered even a modest gain. The teenager's blueprint, once dismissed as youthful enthusiasm, transformed into a topic of serious conversation among supervisors who recognized that innovation seldom arrived in perfect packaging. And the looming necessity of proving whether the idea could work became impossible to ignore. Each of these angles, leadership's willingness to gamble, the enemy's production challenge, and the moral tension inherent in building machines of war, prepared the ground for the moment when theory would collide with reality. The blueprint could no longer exist as a drawing pin to a drafting board or as a subject of quiet debate. It needed to be tested. A section of the assembly line would be halted. Jigs would be rotated. Workers would be reassigned. Observers with notebooks and stopwatches would gather behind marked lines, waiting to see whether a teenager's unlikely solution could withstand the unforgiving demands of a real wartime factory floor. And as the preparations began, the factory braced itself for a turning point, one that would change not only the rhythm of production, but the future of every aircraft that passed through its doors. The day chosen for the trial began without ceremony, marked only by a notice quietly pinned to the bulletin board outside Assembly Bay 3. Workers arriving for the morning shift paused to read it, exchanging puzzled glances. The announcement was brief: a temporary halt in production, authorized reconfiguration of jigs, and the introduction of a revised assembly procedure for the wing section of the plant's primary fighter aircraft. No explanation accompanied the message, but the rumors that had been circulating for weeks suddenly sharpened into focus. This was the test, an evaluation of the teenager's blueprint. Few admitted their curiosity openly, yet more than one veteran riveter lingered near the bay, waiting to see what would unfold. When the line finally shut down, an unfamiliar quiet settled across the space. The usual thunder of rivet guns faded, replaced by the metallic echoes of mechanics loosening fixtures and technicians aligning new jigs according to the redesigned layout. Supervisors consulted the blueprint repeatedly, their fingers tracing the sequence of operations that now diverged sharply from habit. The first sub-assemblies arrived from upstream workstations, each component machined with tighter tolerances than usual, reflecting the blueprint's insistence on precision before assembly. Workers examined the parts with cautious interest. They looked ordinary enough: ribs, spars, brackets, skin panels, yet their edges and references seemed almost unnervingly exact. At precisely 9 o'clock, the lead supervisor signaled for the trial to begin. A stopwatch clicked to life. The crew assigned to the test, handpicked for their skill and adaptability, stepped into position. Some wore skepticism plainly. Others masked their uncertainty behind professional discipline. No one expected miracles. They simply hoped the experiment would not create more work than it saved. The first steps unfolded with surprising smoothness. In the standard process, workers aligned ribs manually, adjusting them by eye and gently persuading them into place with soft mallets. Today, the ribs slid into the jig and seated themselves with an audible click, guided by interlocking reference points built into the redesign. The workers exchanged glances but continued without comment. The spars followed, meeting the ribs in clean, precisely matched joints. A veteran on the team paused, inspecting the fit with practiced skepticism, searching for the misalignment he knew should be there. But the parts held fast, straight, and true, as if the structure itself wanted to assemble. Observers leaned forward as the operation advanced faster than expected. The crew riveted the first connections with a brisk efficiency, free from the hesitation that usually accompanied uncertain alignment. The stopwatch ticked on while supervisors scribbled notes, their expressions shifting gradually from neutrality to quiet astonishment. By the time the subassembly was completed, the team had shaved nearly a third off the usual time. But the true test lay ahead, integrating the completed subassemblies into the wing's main structure. Historically, this stage had been the most temperamental, requiring careful muscle and experience to coax stubborn components into place. Today, the workers approached the task with restrained caution. They lifted the first completed module into position. It settled into the receiving structure with surprising ease, locking into the alignment features designed into both components. A few gentle taps secured the fit. The jig did the rest. A hush spread across the bay. The crew stepped back, briefly suspended in disbelief. It had worked cleanly, naturally, almost effortlessly. The supervisor checked the measurements twice, then a third time. Everything fell within tolerance. No rework was needed. The stopwatch recorded a time that would have seemed absurd if it were not written plainly in black ink. The process continued, each step reinforcing the sense that something extraordinary was happening. Subassemblies joined one another with the same precision. Rivet teams moved efficiently along the structure. Inspection crews found fewer discrepancies than they had ever recorded. A rhythm emerged, different from the old rhythm of improvisation and adjustment. This one was smoother, more confident, guided not by chance but by intention embedded in the design itself. When the final panel went on and the wing reached structural completion, the bay fell silent. All eyes turned toward the supervisor holding the stopwatch. He clicked it off slowly, as though reluctant to confirm what everyone already felt. The time was not merely better than the old method. It was transformative. Hours had been carved away, replaced by a logical, predictable sequence that workers could refine further with practice. No one cheered. This was not a place of celebration, but the solemn exchange of looks between supervisors, engineers, and workers carried a weight more profound than applause. The experiment had succeeded. A teenager's blueprint, once dismissed as unrealistic, now stood validated by the very hands that assembled the aircraft. Yet the trial was only the beginning. As word spread through the plant, expectations shifted. Managers realized that adopting the new method across multiple lines could change production forecasts drastically. Workers sensed that their routines were about to evolve in ways they had not imagined. And somewhere in the drafting department, the young engineer who had dared to question tradition waited quietly, aware that his idea had stepped from paper into reality, and that the next phase, the scaling of his breakthrough, would determine whether the factory could transform its entire approach to building wings. The day after the trial, the factory moved with a different pulse. News of the accelerated assembly time spread quickly through halls lined with tool cabinets and stacks of aluminum sheets. It was not announced officially, not yet, but workers felt the shift in the cautious excitement of supervisors and the uncharacteristic haste of department heads moving between meetings. Something significant had happened in Assembly Bay 3, something that hinted at a future none of them had expected to see so soon. Production logs were rewritten. Engineers drafted memos at a pace that matched the urgency of the new reality. And at the center of it all sat a blueprint that, only weeks earlier, had been the least promising document in the drafting cabinet. Management convened before the first shift had even begun. They reviewed the trial data, time reductions, defect rates, alignment accuracy, rework statistics. Every number pointed in the same direction. What had once been a theoretical improvement had materialized into a measurable advantage, and in wartime production, a measurable advantage was never small. The decision was reached faster than anyone anticipated. The method would not remain confined to a single bay. It would be expanded first to a second line, then to the entire wing assembly division. The transition was not simple. Jigs had to be duplicated or rebuilt to follow the new alignment logic. Machining schedules were revised to ensure upstream components met the tighter tolerances required by the process. Workers underwent training sessions, some brief and practical, others more extensive, as the new system demanded different sequences and a different relationship with the structure itself. Yet despite initial apprehension, adaptation came quickly. The layout of the workstations began to change, reflecting the modular approach embedded in the blueprint. Tools were rearranged. Fixtures were standardized. The once familiar choreography of assembly evolved into something more deliberate, more predictable, and ultimately more efficient. As the revised lines resumed operation, the results were unmistakable. Wings moved through the factory with a fluidity that had previously seemed impossible. Sub-assemblies arrived on cue, each one fitting precisely into the next like pieces of an intricate puzzle. The bottleneck that had strained production forecasts for months began to dissolve. Where delays had once stacked up like driftwood against a riverbed, the new system created a steady current of progress. Supervisors marked off completed units on large wall charts at a pace that seemed almost surreal. Meanwhile, outside the factory's brick walls, another transformation unfolded. Air Force liaisons who monitored production capacity took notice of the sudden acceleration. Initial reports were cautious, citing improved assembly efficiency without naming its origin. But as output numbers climbed, their tone shifted. Squadrons training across the country began receiving replacement aircraft sooner than expected. Maintenance officers, accustomed to long waits for new airframes, found their inventories replenished before shortages could disrupt operations. Even pilot instructors remarked that rotations felt smoother, as if the entire pipeline had gained momentum. In Washington, procurement officials updated projections that had once drawn uncomfortable scrutiny. The factory, once considered vulnerable to falling behind schedule, became an example of rapid adaptation. What impressed the most was that the improvement did not rely on vast capital investment or revolutionary technology. Instead, it emerged from a fundamental rethinking of how wings were assembled, an insight that echoed the growing belief that industrial war would be won not only by innovation in combat aircraft, but by innovation in the way those aircraft were built. Through all of this, the young engineer remained almost invisible to the broader machinery of bureaucracy. His name appeared in internal memos and in small acknowledgments on technical change orders. But beyond that, recognition was limited. He watched the changes unfold from the drafting room, observing as the lines he had drawn in pencil became physical routines practiced by hundreds of workers. Occasionally, he visited the assembly bays, standing quietly behind safety lines while teams executed the process he had once only imagined. To the workers, he was simply another engineer, young, earnest, and respectful of their craft. Few knew how fundamentally he had shaped the new rhythm of their labor. Yet even without ceremony, the magnitude of his contribution was unmistakable. The factory was producing wings faster than ever before, and the effect compounded daily. Every completed wing meant one more aircraft closer to combat readiness. Every reduction in assembly time meant an incremental advantage in a war increasingly defined by industrial capability. The teenager's blueprint had become more than a clever idea. It had become a strategic asset woven into the fabric of the nation's war effort. As winter settled over the continent and the pressures of global conflict continued to build, the factory's transformation stood as a quiet testament to the power of reimagined design. What had begun as a single experiment now shaped the output of an entire production line. And the full consequences of this momentum, industrial, strategic, and human, were only beginning to unfold, waiting to reveal themselves in the months that followed as the war's demands grew more severe. The first major production reports issued after the new assembly method took full effect left little room for ambiguity. Output had risen, not marginally, not gradually, but decisively. Where the factory once struggled to complete a predictable number of wings each week, it now exceeded targets with a consistency that startled even the most optimistic managers. The backlog that had clogged storage areas and tied up valuable floor space began to shrink as finished wings rolled steadily toward final assembly. Within weeks, the cadence of the plant had changed so thoroughly that it became difficult to remember how chaotic the old rhythm had been. The numbers told the story plainest. Reduced man-hours per wing, lower defect rates, shorter inspection cycles, and a measurable drop in rework orders. These improvements did not merely reflect a smoother process. They represented aircraft that could take flight days or even weeks sooner than before. Military officials watching the data unfold understood the significance immediately. Replacement fighters had been a persistent concern, especially as training accidents, mechanical wear, and expanding squadrons stretched available resources. Now, deliveries from the plant gained a reliability they had never achieved, reinforcing the Air Force's growing confidence that industrial capacity could match strategic ambition. Commanders began planning with a new sense of possibility, no longer fearing that frontline units would be forced to fly aging aircraft simply because logistics could not keep pace. The transformation was subtle at first, but as the months passed, it became clear that the improved production rate was reshaping expectations across entire commands. The war was increasingly a conflict of volume and endurance, and any innovation that increased the tempo of aircraft replacement quietly shifted the balance. Back at the factory, the workers themselves felt the change in their daily routines. Where once they had confronted constant frustration, misaligned ribs, stubborn spars, panels that resisted fitting, they now worked with assemblies that fell into place with an almost effortless logic. The new method reduced not only time but strain. Riveters no longer hovered anxiously over uncertain joints. Fitters no longer fought metal that seemed determined to resist them. Inspectors, accustomed to marking frequent corrections, began recording cleaner reports. The shift in morale was unmistakable. Crews who had once joked darkly about the impossibility of meeting quotas now spoke with a growing pride, recognizing that they were participating in a process that actually worked with them rather than against them. The teenagers' blueprint had not just reorganized metal. It had eased the human burden that the old methods had quietly imposed. Recognition for the engineer responsible came slowly and in modest forms. His supervisors, once skeptical of his observations, now requested his input on minor revisions and additional efficiency improvements. He received a promotion that lifted him from the ranks of junior drafting staff into a position where he could contribute more directly to production planning. There were no speeches, no awards, no public announcements. Such gestures were rare in wartime factories, but those who worked closest to the blueprint understood what he had accomplished. The mid-level manager who had championed the trial sought him out one afternoon, offering a quiet acknowledgement that carried the weight of genuine respect. It was a simple conversation in a corridor lined with tool crates and safety posters, but marked a turning point. The young draftsman was no longer an anonymous figure at a back table. He had become a recognized contributor to the factory's success. Still, the most profound recognition came not in words, but in the expanding network of workers whose tasks had been simplified, whose frustrations had eased, and whose efforts now translated more effectively into the aircraft rolling out of the plant. They did not know his full story, nor did they need to. What mattered was that the wings they built came together smoothly, cleanly, predictably, and in the subtle ways that factory communities form their own quiet narratives. The blueprint's creator became part of the internal folklore, spoken of not with admiration alone, but with gratitude. The war pressed on, and the factory pressed with it, but the memory of the transformation lingered as a reminder that sometimes the smallest ideas, born from observation and humility, could reshape the labor of thousands. The effects of a new process continued to ripple outward, setting the stage for broader shifts that would extend far beyond the walls of a single plant. And as output increased and confidence grew, the story of how one blueprint had redefined efficiency would soon merge into a larger industrial awakening that touched not just wings, but the very philosophy of wartime manufacturing. As the factory settled into its new rhythm, the ripple effects of the teenager's blueprint expanded far beyond the immediate improvements to wing assembly. Other divisions began to take notice. Maintenance crews in the jig shop observed that the modular alignment philosophy could be applied to fixtures used for fuselage panels. Foremen in the tail assembly section wondered whether standardized attachment points might ease their own recurring bottlenecks. Even outside suppliers, informed of the factory's tighter tolerance requirements, adjusted their machining practices to support the new precision-driven workflow. It was not long before conversations and engineering meetings shifted from isolated troubleshooting to a broader reconsideration of what production could become if every component, every sequence, and every tool were designed with assembly in mind. What had begun as a single solution to a single problem quietly evolved into a guiding principle. The factory was no longer just building airplanes, it was beginning to think like a modern industrial organism. Military officials, always attentive to innovations that improved output, soon initiated inquiries into how the method might translate to other plants. Representatives toured the facility, walking slowly along the reorganized bays, studying the spacing of jigs and the choreography of teams who now moved with confidence through their streamlined sequence. They asked detailed questions about cycle times, torque patterns, and inspection intervals, seeking insights that could be carried to other production centers. Some plants adopted the method cautiously, integrating elements of modular assembly without fully abandoning older habits. Others, facing their own production pressures, embraced it more aggressively. The influence grew not through mandate, but through necessity, spreading organically across a network of facilities with shared goals and shared constraints. In this way, the blueprint's logic became part of a quiet transformation that strengthened the nation's industrial backbone. Beyond immediate wartime needs, the method also reshaped thinking about design itself. Engineers began to acknowledge that the ease of manufacturing was not a secondary consideration, but a core element of successful engineering. Drawings that once prioritized theoretical purity now confronted a new criterion. Could this be built quickly, reliably, and repeatedly by the thousands? Younger designers, inspired by the teenager success, approached their work with a heightened awareness of assembly flow. Older engineers, though slower to adapt, gradually recognized that the demands of modern air warfare required more than mastery of aerodynamics. They required mastery of production. This shift in mindset planted the seeds of what would later evolve into formal concepts of design for manufacture and assembly, decades before such terminology entered common use. The broader strategic consequences were equally significant. As production efficiency improved across multiple plants, aircraft availability grew more stable. Squadrons deployed overseas received replacement machines faster, reducing downtime and sustaining operational readiness at critical moments. The logistical networks supplying the war effort became more resilient, no longer strained by erratic delivery schedules or unpredictable shortages. Each improvement reinforced the others, forming a cycle of reliability that contrasted sharply with the mounting pressures faced by enemy industries struggling under bombardment, resource scarcity, and dispersed manufacturing. Industrial power, long theorized as a decisive factor in modern war, now demonstrated its influence with unmistakable clarity. Yet amid these large-scale outcomes, the story retained a human undercurrent that never quite disappeared. Workers spoke of the changes with a mixture of pride and disbelief. Managers who once braced for missed quotas now focused on refining processes instead of scrambling to compensate for inefficiencies. The teenager at the center of the transformation continued his work quietly, contributing new refinements as he gained confidence and experience. He remained aware that his innovation, however impactful, was only one piece of a much larger machine. The war was not won by a single blueprint, nor by a single factory, but by countless acts of ingenuity that accumulated into overwhelming industrial momentum. As months passed and the factory settled deeper into wartime routine, the blueprint faded from daily conversation, becoming part of the operational fabric rather than a celebrated breakthrough. But its influence endured in every wing that moved smoothly through assembly, in every aircraft that rolled out of the hangar ahead of schedule, and in every squadron that gained strength from the steady flow of machines delivered to them. It marked a quiet turning point in the war's industrial narrative, a reminder that progress often arrives not through dramatic leaps, but through a simple, well-considered improvement that reshapes the work of thousands. And in this evolution, the stage was set for reflection on what such a transformation truly meant, both for the war and for the people who labored through it. When the war eventually drew to its uneasy close, few people remembered the precise day when a single blueprint altered the rhythm of an entire factory. The world moved on, counting victories and losses in sweeping statistics, rarely pausing to consider the small, almost invisible innovations that had shaped the outcome. Yet in quiet corners of industry, where aluminum dust once clung to clothing and the hum of machinery filled the air, the impact endured. The teenager who had dared to redesign a process older engineers accepted as immovable grew into a seasoned professional, carrying with him a lesson that would guide his entire generation of post-war engineers, that the way something is built matters as much as the thing itself. Factories that had once strained under the weight of wartime production gradually shifted to peacetime manufacturing, but the logic of modular assembly, of designing structures that fit together cleanly, predictably, and efficiently, remained. It appeared in commercial aircraft, in the expanding automotive industry, in the emerging world of electronics. The idea that components should snap together with minimal struggle became not a novelty, but an expectation. What had once been an audacious simplification applied to a fighter wing quietly evolved into a guiding philosophy for modern industry. And yet, beyond its technical legacy, the blueprint carried a more human meaning. It served as a reminder that innovation does not always come from authority, nor from experience alone. Sometimes it emerges from someone young enough to question what others accept without examination. Someone willing to observe carefully, think differently, and place a new idea on a crowded desk even when no one is waiting for it. In the vast machinery of war, shaped by generals, politicians, and industrial giants, it is easy to forget the role of individuals whose contributions are measured not in speeches or headlines, but in minutes saved, errors avoided, and lives indirectly touched by the machines their hands helped build. As the last wartime aircraft were retired and replaced by newer designs born in a different era, the factory's transformation remained woven into history not through grand commemoration, but through the quiet truth that the simplest improvements can become the most enduring. A wing that once took days to assemble could now be completed in hours. A war fought across continents had turned, in part, on the efficiency of a process imagined by someone barely old enough to vote. And in that contrast, between youth and responsibility, between the smallness of a blueprint and the scale of its impact, lies the enduring lesson of how ingenuity, even in its humblest form, can reshape the world.